All right, so the topic of the day, topic du jour, is vapor power cycles, which is the name of chapter 8. Vapor power systems, I guess. Power cycles is essentially what it is. So, so far in this class, what we have done is we have kind of taken components as their own little system, and we've done a little bit of analysis on them, right? That's sort of what we've been doing. Now, what we are going to do is we are going to look at entire cycles as a system, and we are going to do those by parts, right? I'm not going to go over too much of this, but essentially what a vapor power cycle is more or less some working fluid is heated up to a superheated vapor using the boiler, which is, these are the terms I've been using the whole semester as to try and bring us to here. Heats it up to a superheated vapor. It then gets expanded through a turbine. The turbine blades spin, which is attached to essentially the grid, right? You know, this is how your power gets to your house after some transforming and things like that to make it home ready. And then what happens is that after it goes out of the turbine, we need to get that steam, whatever mixture it is, right? Either be superheated or, you know, whatever comes out, usually saturated or superheated still. We need to get that back to the first state, right? Because, you know, it's not a cycle unless it gets back to the first state, right? So we have to find a way to get it back to the first state. And so how we do that is we then run that through the condenser. Now, I've mentioned that there is and this is a basic power cycle, by the way. These are the basic ideas, but there's other variations of this that have a lot of other parts into it, but this is just the basic one, is that we run it through the condenser so that it loses all of its heat to the environment, and so now we're just at water, right? We just want saturated liquid. Because the next part, for this thing to be pumped through our system, to go through a pump, it has to be liquid, because pumps, obviously, we've discussed this, are for liquid, and compressors are for air or like vapor, right? And so we want to make sure that we get it all the way back up to the beginning, and then we pump it all the way back into the boiler, and then the boiler superheats it again, and that creates the cycle, right? It just does that constantly. And in your next class, Thermo 2, I really wish that COVID-19 wasn't going on, because you guys would have a chance to probably go into the power plant, and you can see the, like, command. You can see, like, the command station, like, where the guy sits there with, like, you know, 8 billion monitors, like Homer Simpson, right? And you can see all the things, the information coming his way. And it's like, it's everything. It's like power generation, like mass flow rates, things like that at all times. It's really cool. But essentially that is like the basis of this chapter, right? Is that it's doing those systems. It's doing doing problems with those in mind. Now, most of your power comes from coal, and we live in an area where coal is rather prevalent, right? As you guys would know, Southern Illinois and this whole area has a pretty high coal reliance, I would say. But then it goes to, and by the way, these might be old stats. This is 2009, so I'm sure other things are going up, like renewables probably have gone up, but, you know, take them for what they are right now. So we have coal at about 50, then natural gas, nuclear, hydroelectric. So hydroelectric, there is a plant that does this in Missouri, which I listened to a guy have a presentation. He was the one that ran the whole plant. He came and did a presentation at SIU. And they're a hydroelectric plant where they just have water rush down into the turbines from like a reservoir, and it spins the blades. And then they pump it back to the top. And then we have other renewables, oil, things like that, right? So this is kind of our breakdown. But essentially, how these things end up working, though, is that this is like the one thing that a lot of people may not know, is that basically, like, these right here are all the same, really. Like these are, so it's just a different type of source, right? So coal, natural gas, nuclear, they're all the same, and even some over here in the renewables might be the same, and I'll explain that in a minute. And what I mean by the same is that they are the process for the plant is basically the same as what I just described, right? It's basically just those major key points. It's the boiler, turbine, condenser, and pumps, right? Now, there's obviously a lot more that goes into it than just those things. Like there's, different piping sizes and things like that. But those are the basic ideas. And they're all basically the same. It's just a different source of energy that goes into the boiler, right? So for the first one, obviously coal fire plant. That is how we get the heat for the boiler. Then over here, natural gas. That is the other one, right? So natural gas is, we'll learn about those in chapter 9, which are gas-powered cycles is the name of the chapter. And essentially, it's the same process, though, more or less, except that it doesn't cycle back to the beginning. At least not in the same way. And then we have nuclear, which is also the same. Once again, all we're doing is turning water into vapor and spinning a turbine blade. The difference is that all three of these are just different ways of getting it through the turbine blade at really high temperature, really high pressure, right? Nuclear does so by nuclear reaction. Natural gas does it by blowing natural gas, burning it. So this is that'll be in a combustor, which is the next chapter, something like that. It's a combustor is what it's called. Little explosions, sort of a ring of fire in there, and it blows up the natural gas. And then coal is obviously the one that we're more familiar with, and even renewables. Now, so the one that I was going to talk about here is that over in Nevada, I actually passed a plant like this. And what it does is that it takes solar energy. So it's a solar array. Essentially what it does is that the sun hits the solar panel, and the solar panel essentially heats up this little pipe, right? It's probably a big pipe, but it's a pipe. And inside the pipe, it's either, I think it's oil or it's water, one of the two. And what happens is that fluid then exchanges heat with the cycle, and then that part of the cycle runs through the turbine. So essentially, it's just using the sun for the boiler instead of these other ones here. But it does throw through like heat exchange between it might use oil, or they might just go direct to water and run it through it. I don't remember which one, but essentially I think both of them exist. But yeah, those are like they're all more or less, they have the same thing in mind. Now, obviously, some of these might be, more clean than others. Maybe you could say, and we might talk about that in Thermo 2 a little more. Probably not me. It'll probably be Dr. Matthias you're with. But yeah, and so as you can see right here, you can actually see. This right here, the Rankine, is the name of the cycle, which you guys obviously know that there's degrees Rankine, which is the absolute temperature for English units. This is named after him, the Rankine cycle. And so the Rankine cycle is the basic cycle that I just described. It's the steam into turbine. And Brayton is the other one, which is the natural gas explosion one. And so these are all Rankine based. This is Brayton based. So like I said, they're all basically the same in how they work, but not maybe in how they operate, right? Like how they are getting started. All right, 1 second before we continue on any further. Give me 1 second. It's a live show, ladies and gentlemen. My tea was overflowing for a second, so I have to take a little bit of a sip. Sorry, lads. That is really hot. All right, so now we're here, considering vapor power systems and introducing vapor power plants. So this is what we wanted to get to today with that background information. It says, referring again to Table 8.2, 7 of the power plant types listed require a thermodynamic cycle, and 6 of these are identified with the Rankine cycle. The Rankine cycle is the basic building block of vapor power plants, which are the focus of this chapter. The components of 4 alternative vapor power plant configurations are shown schematically in order in Figure 8.1. In order, these plants are fossil-fueled, nuclear-fueled, solar, thermal, and geothermal. So the one that I described, which was the solar one, is the solar thermal. This is the one that the sun heats up the working fluid. But then obviously you guys would think of photoelectric. I think is that the other? No, it's not photoelectric, is it? Photovoltaic, is that right? I think it's photovoltaic. Someone corrected me about this a long time ago. But essentially, those ones are the ones where the actual silicon and I think it's the actual silicon and the process they use to make it is a semiconductor or something. I can't remember exactly how it works, but essentially it creates charge through the sunlight. And so that's a different one than this one right here. Essentially, solar thermal is just mirrors, more or less. They're kind of mirrors. And they just are directed at one point. And then it says, in Figure 8.1a, the overall plant is broken into 4 major subsystems identified with the letters A through D. These letters have been omitted in the other 3 configurations for simplicity. The discussions of this chapter focus on subsystem B, where the energy conversion from heat to work occurs. The function of subsystem A is to supply the energy needed to vaporize the power plant working fluid into vapor required by the turbine subsystem. So working fluid is a term that we are going to use a lot in Thermo 2. Essentially what it means is whatever the power plant runs on. So, or whatever is running inside of the cycle. So for example, for a lot of Rankine cycles, you use water, right? Water is it's available, right, all over the place. So water is something you would use. But some systems don't just run on water. So you do have to be careful and not always assume, but essentially the working fluid is whatever is currently running in the cycle. All right, and then it says, then we have, so this is the picture they were talking about right here. So I'm going to zoom out just a little bit because there's a lot going on here, right? So this right here is our, this is more or less our Rankine cycle for coal. Okay. Fossil fuel power plant. So essentially, like I've said before, is that you have your boiler going in here, right? And more or less it's an air fossil fuel mixture and it just heats up, right? This is like, it's very hot in the boiler, and also the boiler is huge. So the last time I went to the power plant, I didn't have to go. What's funny is I've actually been like 4 times because I was a TA for Thermo 2 a couple of times. So I've actually been a large amount. And the last time I went, the only reason why I went was because they allowed us to go into the boiler, which I had never done before. They were doing maintenance. This boiler is massive. We're talking like multiple stories tall, just an empty chamber in there, like except you can see like the holes where like the where the fuel comes in. It's really cool. Very hard to get into though for someone as tall as me. If you guys are tall, you guys might have problems, but it was a very tight squeeze. So then let's follow the circuit around. So in here, there's a heat exchange process going where the water is being heated up. And then once it gets superheated, it goes through the turbine here, right? And the turbine is connected to a shaft, which is hooked up to an electric generator, right? And then this is how you get your power out, essentially, because this right here is connected to the grid. Like, there's transformers and a bunch of other things that are attached to the outside, but that's not really part of the cycle, per se. It's just part of what happens later. Then, after the turbine, it goes through the condenser here, right? Now, there's a couple ways that this could happen. So this one shows a cooling tower. So cooling towers, as maybe some of you know, are these big smokestack looking things that you see whenever there's like a movie of a nuclear plant. There's always big cooling towers, right? A lot of people don't understand is that this isn't actually really. This has nothing to do with because they look ominous, right? Like when you look at one of these, you're like, holy crap! Like look at that big, tower, all the smoke coming out, right? it's a nuclear power plant. It looks dangerous. It's not though. Essentially, what's happening in here is this is basically just like steam. It's like water. It's water vapor. So it's not actually anything bad. So it just looks like that from the outside. But essentially, this is a cooling tower. And if you do Thermo 500, you analyze this stuff right here, which is really cool. You actually have to do a question about cooling towers, like how much water is falling down. Like it's a psychometrics problem in a lot of ways. Psychometrics being the study of humidity. But essentially, what happens here is you could replace this cooling tower with a lake, right? This could be a lake here, and it's just water running in circuit, right? Because as you can see, what happens here is that this is the hot water, and it comes out through these little sprays, and what happens is that air is coming up this way, and it's rushing in, and it's cooling this down, and then it becomes water right here. It like condenses out, essentially. Like condenses out. The water condenses out, and it becomes water, like a pool down here, and then it goes back in. That's all a cooling tower is. But so it's a way of cooling the working fluid, which is the same thing as having a lake here. It's the same thing. You just run water in circuit. Then, after it leaves the condenser at a liquid of some sort, saturated liquid probably, or less, it goes into a pump. And the pump's job is obviously to feed it back into the boiler, right? And then we're back to the start. So this right here, for everyone wondering, this right here is the basic Rankine cycle that you will do questions on. So there's one state here. This will be 2, this will be 3, and this will be 4. And so you have to solve enthalpies and entropies for those 4 states, more or less. And then this one right here is just is the nuclear reactor. I'm not as my buddy Austin, who is he online right now? No, he's not. He works in one of these plants, and he would probably know more about how they work, just due to like how him working at one, especially the reaction part. Like so, essentially, this is the exact same thing right here. You have source of heat, which is the reactor. Or no, well, it is the source of heat essentially. But then you have the boiler here. These are the rods, right? So you guys have always heard about the rods, like I think it's the control rods or whatever they're called. This is where like the material is actually happening for the generation, and so it kind of works the same way in this weird cycle, but then it once again goes into a turbine and then condenses out into a pump and then comes back into here. So it's very similar, but I think this one's probably more technical, obviously. And then this is the one that I was talking about earlier, where the solar array is all bent to reheat this pipe. So you can see right here, this is the pipe carrying, it says molten salt or oil, so it's either like a brine or an oil. And that's for heat transfer properties. So I think what they do is they take a molten salt or an oil that has high heat absorption, specific heat probably, and then they throw it in over here and they heat it up, and then they run it in tandem over here with the water, so it heats it up. So it's just essentially the difference between these, as I said before, is the heating of the fluid. It's how did you heat the fluid. And then we finally got to my favorite one, because I did a presentation on this like 2 years ago, and it was hilarious. I still have the slideshow. It was a great time. I had the whole class laughing. It was great. I managed to slip in the 4 elements from Avatar: The Last Airbender on the slideshow. It was pretty good. So essentially what happens here is that you have hot steam, or underground, right? So essentially what happens is that your fluid, whatever it is, either water or something else, is being brought from underground, because, as you guys probably are aware, the further you go underground, right, it's like higher pressure, it's higher temperature, right, as you get closer to the core. So what's happening is that they're just using this as the loop. So we're getting heat down here, and then you're pumping it in here, and you're heat exchanging with what's ever in the working fluid. So once again, instead of coal fire, instead of nuclear reactor, instead of solar power, it's just a fluid going down into the ground and coming back up really hot and then running in here once again. So same as before. And there's some environmental things that you will probably go over more in depth with Dr. Matthias because, full disclosure, he's brilliant and he goes over these things a lot more in depth than I will because we're just trying to get to the basics here. But yes, we always talk about the environmental effects. All right, so then we have the Rankine cycle. So this is the Rankine-based cycle that we're going to start with. And so it says, referring to subsystem B of figure 8.1 again, observe that each unit of mass of working fluid periodically undergoes a thermodynamic cycle as it circulates through the series of interconnected components. This cycle is the Rankine cycle. Important concepts introduced in the previous chapters for thermodynamic power cycles generally apply to the Rankine cycle. And it says, the first law of thermodynamics requires that the net work developed by a system undergoing a power cycle must equal the net energy added by heat transfer to the system. The second law of thermodynamics requires that the thermal efficiency of a power cycle be less than 100%. True. All true. Right? So I'm going to go back up to that picture. So this is what they are talking about right here. Again, I'm going to outline it. This is the Rankine cycle. And so what they said in those two parts, the first and second laws of thermodynamics, in respect to this, they only mentioned the corollaries that mattered. Essentially what it's saying is that if this cycle exists right here, the highest amount of energy we could ever get out of this cycle is right here. Essentially, it's Qn, right? Because this is what's powering the cycle, right? This is what's heating up. Let's say we had a 100% heat transfer rate from the boiler to the water, and then from here to here, to going into the turbine, and the turbine was had a 100% transfer rate. That is the highest we could ever get. There's no other way to deny it. It is the highest we could ever do. So the net heat added, right, is the energy of the cycle. Is what determines how the cycle runs. And then the other one is the thermal efficiency. So obviously, due to losses and a bunch of other things, right, like turbine work and condenser heat transfer and a bunch of stuff, right? Heat's going to leave. We're going to lose work due to friction and a bunch of other things. The thermal efficiency of this power plant is not ever going to be 1. Most cycles, I think for Rankine, I don't want to be wrong about this, but I'm pretty sure they end up being in the, I would say I want to say 40. I know mid 30s to 50, mid 50s is probably where you would expect. I know that Dr. Matthias always mentions whenever they have a big breakthrough where one power plant was able to get 70-something%, which you guys might be like, well, 70% out of 100, that's a C, right? That doesn't sound that great. But it's also really amazing to consider that. That's incredible. So that means that essentially what's that saying for you guys is essentially it's saying is that the work of the cycle, the net work of the cycle, was 70% of the amount of heat that went in, which is an incredible ratio, right? I mean, that's incredible. If you look at cars, right, like auto cycles, like how your car runs, I know they're not the same, but car cycles don't run anywhere close to that, I don't think. But anyway, let's go. So right here, let me see. So it says modeling the Rankine cycle. So this is the last thing that we wanted to get to today, was modeling the Rankine cycle. It says the processes taking place in a vapor power plant are sufficiently complicated that idealizations are required to develop thermodynamic models of power plant components and the overall plant. Depending on the objective, models can range from highly detailed computer models to very simple models requiring a hand calculator at most. That's where we're going to live, guys. We're going to live right here in the hand calculator at most category. Study of such models, even simplified ones, can lead to valuable conclusions about the performance of corresponding actual plants. So someone that I did my thesis with, so he wasn't part of my thesis, but he was someone that was in the class with me. He did I think an exergetic analysis of a power plant, which is essentially what exergy is. Trying to think of it's essentially the concept is how much work could you have done, right? Like how much did we? Essentially, it's like what we could have done. It's like a higher limit, and so he did an analysis of a power plant, and he did a whole one, like a real power plant too. Like it was extremely thorough. So I'm sure he got his degree. It was pretty good, but essentially that is the complicated model. And Dr. Matthias has had a student do the Lake of Egypt power plant. He did an analysis of it as well to tell them. Essentially, he told them like where they were losing their most power, right? Like where were they losing their most energy so that it could turn to power. And he was telling them certain spots that these are the places that you should invest in further to get more out of it, right? So that's what a in-depth analysis would look like. All right, and then it says, thermodynamic models allow at least qualitative deductions about how changes in major operating parameters affect actual performance. They also provide uncomplicated settings in which to investigate the functions and benefits of features intended to improve our overall performance. So this is essentially what I just said, is that you do like you do a good analysis of a power plant, and you can kind of tell where they're losing their most. Their potential is lost, right? And it says, whether the aim is a detailed or simplified model of a vapor power plant, adhering to the Rankine cycle, all of the fundamentals required for thermodynamic analysis have been introduced in previous chapters. They include the conservation of mass and energy principles, the second law of thermodynamics, and the use of the thermodynamic data. These principles apply to individual plant components such as turbines, pumps, heat exchangers, as well to the overall cycle. And then it says, let us now turn to the thermodynamic modeling of subsystem B, figure 8.1a. The development begins by considering in turn the four principal components. So you have turbine, condenser, pump, and boiler. So these are, like I said, the four major, the four elements live together in harmony. The Fire Nation hasn't attacked yet. So then it says, then we consider important performance parameters. Since the vast majority of a large-scale vapor power plant use water as the working fluid, water is featured in the following discussion. For ease of presentation, we also focus on fossil fuel plants, recognizing that major findings apply to the other types of power plants shown as well. All right. So here we go. It says, the principal work and heat transfers of subsystem B are illustrated in figure 8.2, which is down here somewhere. In subsequent discussions, these energy transfers are taken to be positive in the direction of the arrows. The unavoidable stray heat transfer that takes place between plant components and their surrounding is neglected here for simplicity. Kinetic and potential energy changes are also ignored. Each component is regarded as operating at steady state. Using the conservation of mass and conservation of energy principles together with these idealizations, we develop expressions for the energy transfer shown on figure 8.2, beginning at state 1 and then proceeding through each component in turn. So right here, this is how you should draw your Rankine cycle, your basic Rankine cycle. So how I would draw it is, and I drew every one of them, by the way, because it does help. You just draw like a little square, have it connected to a little, I don't know, is that a rhombus, trapezoid, whatever it is. Someone tell me in the chat. And then you have it going into a long. You could draw this one as a little square, or like a something like this, just to not confuse yourself. But but I'm going to do a little narrow one like that. And then over here, you usually do a circle for the pump. And you go back up, and you draw your state points. You go 1, 2, 3, and 4. And so this right here is your basic vapor Rankine cycle. Now, obviously, your results may vary. It might look better or worse, depending on your artistic talent. But that is all we need, right? That's it. So, now let's look at the first one. So the turbine. It says vapor from the boiler at state 1 having an elevated temperature and pressure expands through the turbine to produce work and then is discharged to the condenser at state 2 with relatively low pressure. Neglecting heat transfer with the surroundings and the mass and energy rate balance for a control volume around the turbine reduces to the following. So essentially what we said is we're not taking in kinetic or potential energy. We've neglected heat transfer to the surroundings. Now obviously in the real cycle, this will be a number, right? There's no way to perfectly insulate this. Turbines are pretty big, very massive structures, and so you can't possibly insulate it perfectly. So this will be a number, but essentially what they're trying to say is that relative to the work out, this number won't be very big, right? So for example, let's say I had let's say I had 100 million or whatever, right? Let's say I have 100 million as work and the heat is 1,000. Those numbers are so yes, this is there, but it's very small relative to that. It sort of is reminiscent of whenever we're talking about velocities with the diffuser and nozzles. It's sort of reminiscent of that, where they will neglect one of these because it's small relative to the other term. So, as you can see, we get rid of this, and get rid of this. And so, the work of the turbine just reduces to what? The change in enthalpy through the turbine, right? So, it is this right here. Work of the turbine is H1 minus H2. And and real quick, all of these are taken to be positive at the start. So for these questions, they will all be positive. So H1 minus H2 is a positive quantity for a turbine, always. And they will put this in the terms that are always going to get you positive. So you should definitely remember H1 minus H2. Now let's move down to the condenser. It says in the condenser there is heat transfer from the working fluid to cooling water flowing in a separate stream. The working fluid condenses and the temperature of the cooling water increases. As steady state, the mass and energy rate balance for control volume enclosing the condensing side of the heat exchanger give the following. So this right here is equal to the heat leaving. So right here, this is the heat leaving the cycle. And it's not like just leaving, right? It's not like just flowing into the ether. It's leaving in the form of water, right? Running through this stream. So don't think of a condenser, and I know we've done a condenser question, but don't think of a condenser as anything different than a heat exchanger. That's all it is. So those heat exchanger questions where we did this, where it's water comes in here and leaves here, comes in here and leaves here, right? At these conditions, this is what that is. Except, so this would be cooling water. So cooling water comes in cold, and then cooling water leaves hot over here. And then this would be working fluid and working fluid 2, right, which leaves colder. Well, okay, it doesn't leave colder because it's just condensing, which means that it's going all the way to saturated liquid. And if you guys obviously know that the saturated liquid, or in the saturated liquid tables, temperature doesn't change inside the saturated region. But yes, it's going to have less energy. How about that? Less energy. Not necessarily colder, less energy. So it just takes heat transfer away. So don't think of anything besides this. Don't think of this as anything different than a heat exchanger, because that's all it is. So the heat leaving is just H2 minus H3, which is a positive. So that'll be a positive value, actually. So this right here, they have them all in terms of positives, but obviously heat leaving is a negative quantity. So you just have to know that. But this is a positive number. They're getting them all positive for you. Now, we go to the pump. It said the liquid condensate leaving the condenser at 3 is pumped into, or from the condenser into the high pressure boiler. So this is this part right here, 3 to 4. And then it says taking a control volume around the pump and assuming no heat transfer with the surroundings, mass and energy rate reduces to. So essentially, all of these things are being applied. Like this equation right here is being applied for each part of this, but they're making assumptions, right? So for the turbine, we got rid of heat, we got rid of all these things over here. For the condenser, same thing. We got rid of velocity, got rid of this, got rid of work, because condensers don't make work. And we just had heat transfer, right? So Q is equal to the change in enthalpy. And the same thing with the pump. So it's H4 minus H3. Now you guys will probably be wondering here, like, well, wait a minute, why did they flip? Because they've all been the one before minus the other one. That's because the work of a pump is negative. So they had to flip it to get this to be positive. So this right here will be a positive quantity. But it is work going in. So here's the thing. You can so that not to confuse you, but you can write this quantity as anything you wanted. So for example, let's say the work of the pump was 100, which, you know, whatever it is, right? Let's say it's 100. You could say work of the pump is, at least in my opinion, you could say something like this. You could say work of the pump is negative 100, or you could say work of the pump is equal to 100 going in. This is the direction, right? Essentially, the negative sign is the direction. Or you could specify if it's positive, you could say work going in to the system, which means that it is a negative quantity, right? So those are the two ways you can do it. Just specify direction. That's all that you need to do, really. And then we have the boiler. It says the working fluid completes a cycle as the liquid leaving the pump at 4, called the boiler feed water, is heated to saturation and evaporated in the boiler. Taking a control volume and closing the boiler tubes and drums carrying the feed water from state 4 to state 1, the mass and energy rate balance gives this. Now, this is a typo. Just to let you know, this is wrong. I'm going to slice through that many times. That is wrong. This should be H4. This should be H4. So they've written that one wrong. Because, so I'm going to ask you guys this, since you guys have been very quiet and probably paying attention, who knows. The amount of heat coming into the system here would be what? It is the two things before and after, right? It's 4 over here and 1 over here. How could the amount of heat coming into the boiler be the difference of enthalpy around a turbine? You see the problem? So it's H1 minus H4. So make sure that doesn't confuse you. This should be H1 minus H4. So let's do that right there. So they messed up there. I'll have to send in an angry note to the publisher. You know what's funny, though, is I guarantee you Dr. Matthias already has. Because I'm telling you, he knows these books like the back of his hand. Like, he probably already has. So hopefully they fix that in further editions. So this right here is the heat into the cycle. Essentially the heat into the boiler, right? And now we move on to performance parameters. So this is how we determine how good a cycle is, right? Like, how do we know how good a Rankine-based power cycle is? Well, you do it the same way we have before, right? You know how we had, like, the efficiency, right? You remember those questions where it was like a Rankine or a power cycle develops this much, right? And this is the heat in and this is the heat leaving, right? You sort of do it the same way, right? More or less, it's right here. So eta, right? So the efficiency of a power cycle, thermal efficiency of a power cycle, is equal to the net work. So once again, it's what you want over what we had to do to put it in, right? Or what we had to put in. So what do we want out of a power cycle? Well, clearly we want the power, right? We want the work. So this breaks down to the following. So work net And we do work net because we're taking into account. So those other questions that we had where it's like power cycle develops this is the heat leaving, this is the heat in. It never said that there was any work being taken, right? We didn't have to add any work to the system in those questions. But in actual power cycles you do. Because there's a pump, right? And probably a couple of them at least. So work net over Q in. Because what we had to put in, I mean, we can go back up here to the picture as well. If you look over here, what is the only thing going into the system? We have work leaving right here. We have heat leaving right here. We have heat input right here, and we had work input here. So, if we go back down here, how this works is you have, no pun intended, you have work net, which is the work of the turbine minus the work of the pump, because it's the net work we had to add, right? And then Q in is just Q into the boiler. So this right here is your thermal efficiency. It is what we got out and what we had to put in, same as all other efficiencies that we've done, right? And how this breaks down to in terms of numbers, which I don't think, you don't really need to worry about that right now, because if you get all caught up in these numbers, like, oh, is it H2, is it H1, like all that, you get confused in later cycles because these numbers change. Because instead of, like let's say it's like boiler here, there could be 2 turbine stages or 3 turbine stages and multiple condensers or something like that, and those numbers change. But what you need to know is, you need to know this part. It is the summation of the work at the top being positive and negative, right? So summation of the work divided by the summation of the heat in. And there could be multiple heat in as well. But for a regular Rankine cycle, it is H1 minus H2 minus H4 minus H3. So this right here is turbine work. This is pump work, right? Turbine work minus pump work over heat in right here. So this is boiler. So H1 minus H2 minus H4 minus H3 divided by H1 minus H4. So they actually got it right here, but they got it wrong up there. Or, just like you do with the other stuff, you can do 1 minus Q out over Q in if you really want to. And that's all that is dividing by, I think you just divide by Q in, and you end up getting, it ends up reducing to 1 minus Q out over Q in. You can do either of them, but this one right here is the one that you should remember the most, probably. Because most questions in Thermo 2 have you go, what's the work? So this is the actual, this is the way the question will go. It'll say, determine the work of the cycle, determine the heat in the cycle, what is the thermal efficiency? So essentially it'll have you find this, and then it'll say, well, now you need to find that. And then it will say, but what's the thermal efficiency? So that'll be parts A, B, and C. So it kind of breadcrumbs you through the question. It says, here's this, now tell me the last one. So it's fairly, they're pretty straightforward, and basically every question asks you something similar to this. I guess you can talk about back work ratio really fast. I might do that. So the back work ratio. So the back work ratio is something that confuses a lot of people because it's something that you don't see very often. It becomes more prevalent in Chapter 9. Chapter 9, back work ratio, you have to do for a lot of cycles. But for Chapter 8, I don't remember doing back work ratio very often. But essentially what the back work ratio is, it is how much of the work did we have. It's a ratio of the work is more or less what it is. It is how much work did we have to put in to the cycle divided by how much work we created. So right here, it is the work of the pump divided by the work of the turbine. And this number should be extremely low because let's say as this number approaches 1, right? So if you like do a limit here, it's like limit, as, BWR approaches 1, that means that essentially you're not creating any power, right? because that means that if let's say your pump was equal, the pump work was equal to the turbine work, it means that you are actually creating nothing. It means that your power cycle is powering the pump only, which is not the point. The point is to make power. So for a back work ratio of a pump in a power cycle like this, a Rankine. So the reason why this, and by the way, really fast, just so everyone knows, we were talking about nuclear power earlier, and guess who shows up? Let me slide him into the frame here. He's in the chat, ladies and gentlemen. So, what I was going to say is that essentially the back work ratio here is not very big, because pumps and Rankine-based cycles do not, okay, in comparison, they don't take a lot of power to what you get out. But in Chapter 9, which is gas-powered cycles, remember, you're using compressors. Compressors are the ones that do gas, and they are a lot more costly. So back work ratios in the next chapter, in Chapter 9, you could see like 40%. Like, it could be like 40% of the turbine work is going to compressors. But in this one, this will be less than 10. Or less than that, probably. But let's put it this way. If you get a back work ratio in a Rankine cycle that's like really high, like let's say it's like 60%, it means you've done it wrong. It means something is wrong. So go back and work on it again. But yeah, that's basically all we wanted to cover for today. And so really fast, I'm going to pull up the homework for you while we are sitting here. So this is, we'll probably do the edit one. I don't know what this one's going to look like. So essentially, this right here, it's a lot of conceptual questions because this is the last homework of the class. The way this one has been done in recent times is that this can count for either a homework score or it can count for a replacement homework. So I could take the best 10 of your homeworks with this one. However you guys want to do it. I'll leave you the option. Do you guys want this to be a replacement? Or do you want this to be another homework score? And also, not doing the homework is not an option on the board. So select one of those. It's not a very long homework, by the way. It's 7 conceptual questions, and then it's 2 just Rankine cycle questions. So it's not very hard. This is a fairly easy question. Replacement? Well, unfortunately, I can't show you the grade book, Tanner. But let me tell you, there are people who have missed homeworks. So we'll probably just go with that one then, I imagine. All right, so this will be a replacement homework. Or maybe, how about this? If, I don't know, well, what if someone's turned them all in? Then they won't do this homework. Maybe it should be an extra credit homework score for the people that have actually done every homework. I'll have to think about it. How about that? I'll think about it. I bet you do, Tanner, because you've turned in all of them, haven't you? So I would say there's a lot of selfishness going on, but that's all right. That's the way it works. So this will be something. I'll have to think about it. I'll talk with the academic advisor, Velcro Shoes, and we'll see how it goes. But that's the end of the video. Thanks for playing today.